No, it must be another department, another school, I think. So is what? Yeah, I'm thinking so too. Yeah. Okay. Yeah, exactly. Okay, I think the streaming is on, isn't it? How is it? How is the quality? Seems that you. It's good. Okay, so I'm gonna put this presentation on, and then we're gonna discuss a little bit.
We have to adjust the camera.
Adjust the camera.
Yes. Because right now you are not in.
Oh yeah, yeah. So it needs to be pointed.
No, no, no.
Laptop. OBS. So the camera is, yeah, there's no cameras at all. So which one is up? How can I, where is my pointer? Here. So this is supposed to be this guy, no? What is it? Dell. Is that a Dell camera?
Yes.
How come it's not showing anything at all? Still nothing. Yeah, this, no, this is, this, no, that one. Yeah, that's the right one. That's the right one. Yeah, that's good. That's good. You can adjust it like a little bit more up because I see from the, yeah, this is perfect. That's perfect. And look at the quality of the camera, looking so strong and fast and young and everything. Smart. Did I mention smart? Okay, so it's good. It's really good. No, but I see that this camera is better than my previous one.
You were insisting on keeping that.
Yeah, and now what I need to do, I need to get the new headset because this is a no good headset. It's getting old. It's getting old because the mic is most of the time is not willing to cooperate for the reason that is unclear. So I just need to get another one. Okay, so last thing is this. All right. This is in a presentation mode here, and now this one. Thank you guys. Thank you so much for your help. Okay, so how did you like about this? Okay.
I don't have the authority to change it however I like. It's just working.
What's this? So what is this showing this incorrect screen? Oh yeah, oh yeah. So you need to duplicate that. Okay. So look,
Problem is with the lamp.
what happened to this computer?
Everything is on.
But how can I put it back on? Oh, there.
But that is the other one, not that one.
Okay, so I guess that I need to do this. Extend, duplicate. Yeah, this is good. All right, guys, how did you find these AI workshops, 3 workshops? Was it worth it?
Bit of work, but what's interesting?
So it was interesting. Okay, so do you think that it was worth to do it?
Yes.
Good to hear.
I want
Good
to
to hear.
fully was I already do a lot of the stuff because I already invest my own time into AI.
Ah, okay. All right. So how you feel about this? You know, what if we're going to make an entire course about the AI in the framework of mechanical engineering to learn about large language models, surrogate models, data-driven models, so on and so forth. Because what we realized from this workshop was that, you know, it's a three, what was it, 6 hours in total is just simply not enough. It's not enough. You are in a hurry and you cannot figure out the things by yourself because, you know, you need to rush yourself and the explanations becomes to be not as detailed that we wanted them to be. So if it will be entire course, you could, I mean, you guys off the hook because you're going to get your degree soon. By the way, guys, if you want to go, you can go. Thanks, guys. Thanks. And we're going to close 15 to noon, I think, roughly that time. So yeah, so what if this will be an entire course about AI? You would consider to participate if you would do your master degree again, but you don't.
What I would suggest, however, that it's a workshop, like maybe 1 to 2 week workshop, like intensive course,
Uh-huh.
where you, for instance, in the summer, where you do this like
Ah,
intensively.
okay. So you feel that that will be the best way to go.
That's the way he did it, because he just had lectures, and then you have like a lot of time to explore like the things he gives you, like the AI things. And doing it like in 2 hour periods is not enough. So doing a workshop like intensively for like 8 hours.
Yeah,
Like,
that will make sense. So you will have like a 1 hour lecture, then several hours for hands-on tutorials.
yes.
That would make sense. That would make sense. But anyways, so like I mentioned, I made a visit in Innsbruck at the time that the third workshop took place. I was opponent in a public defense, doctoral dissertation defense. And these guys are very much advanced in large language models. So they are looking the ways that how they can automate creating different kind of multi-body models using large language techniques. So they're using ChatGPT, but many, many others, and then comparing which one is the most efficient in a way that can introduce less errors, can make it more accurate models. And now they're looking the ways that they make like hand sketch, like 4-bar mechanism, putting a little bit of dimensions to this 4-bar mechanism, and then take a picture and say to the large language models, okay, here is a mechanism, make a model for me. It's not working perfectly because some cases it's not able to make right kind of the interpretation, but some cases it seems to work okay. And again, it's not going to be something that is going to solve your life completely, but it's like a good assistant, somebody that can help you to get started. And in a modeling perspective, the first attempt made by large language models may not be perfect yet, but this is something that you keep on improving by yourself, or you can give this task to the large language model saying, hey, not good, keep on doing this and that. And that seems to be a pretty efficient thing to do. And that might, or actually will, impact your engineering life quite a bit, because everything that smells mechanical, even remotely mechanical, can be optimized. I'm thinking that, if you take a typical company, there is an army of engineers doing nothing but SolidWorks drawings or another CAD software. They do just a different kind of three-dimensional drawings. So I'm thinking that this is one of the things that can be, if not fully optimized, at least partly optimized, I think. PLM, maybe that could be something that could be optimized, at least in certain perspectives. Now, PLM could be something that there is what is a big dream at the moment is to build instructions, assembly instructions along with the assembly pictures. What you can do with a PLM at the moment is that you can combine different three-dimensional representation of machine, and you can show how it is, how you can put them together. I mean, how it looked when you put them together, but you have still not able to give instructions how to do the assembly work itself. And right now there is this technology that you can somehow have this human character that is showing you first need to take this knot, put that in this bolt. The next thing is that you take this component, put it there, and it's showing like real cartoon or video how to do the assembly work. They've been dreaming to do this already quite a while, but it's so work intensive that it makes no sense because you need to do so much work to do these instructions. So it's better to take a person and make a video. But maybe this is going to change it. Maybe. All right, these are the stuff we're going to discuss end of the course, like all kind of different future perspectives. So what I see how the life might be changing soon. I hope the way that I'm thinking that is going to change soon. But prior to that, one more hot topic. And the hot topic is going to be this eigenvalue analysis and model reduction techniques. I checked the lecture that was delivered a week ago. When was it? Not when was it? 5 weeks ago, because it was just before this AI workshop. It was delivered by Suraj, and he started this finite element method. And finite element method is one of the fundamentals in mechanical engineering. It's used in so many different purposes. And what are these different purposes? We're going to learn them more next week. But we need to take a look at something that is important for us. And something that is important for us is eigenvalue analysis, and not just an eigenvalue analysis, but how is it we can do model reduction. Have you took a Jussi Sopanen's course about machine, what is it, machine dynamics? So is Jussi model reduction Sopanen. So his middle name is model reduction. So he's using a lot of stuff that is model reduction, and he's always speak about model coordinates. So it's almost like Jussi model coordinates Sopanen. So he's an awful lot of discussion about that. So if you took this course, you already have a good understanding what it means. What is, when we're moving from nodal space to modal space. Here we have to do it. There's no other way. We need to do it. And I'm going to explain to you momentarily why we need to do that. Okay? Right. Now, but prior to that, let's summarize a little bit. Let's summarize. Okay, so not looking too good. Oh, it's looking actually good. So it's, okay, so finite element method. So you learned about the finite element method. Now, it's a very often used method in many different purposes to solve many different kind of the problems. And you learn that the finite element method is something that consists of elements, not the big surprise, as the title already implies that this is element-based. And these elements are connected together in nodes. Really what finite element method is about is how you define the life between the nodes. So it's like you have the 2 points, and what you really are interested, how is a life between these points? And this life between the points is something that is it's like inherent feature or telling feature of how is a finite element method. It tells about the convergency, accuracy, how it can be used, and so on and so forth. So everything is between life between these points. So that's extremely important. And you learn that this life between the points is based on polynomials, polynomial expansion. Could be based on that. It's not necessarily the case like that. There's techniques like this isogeometric analysis, which is a finite element based. That too is based on elements and nodes. But the difference between that method and conventional finite element method is that this life between the points is not based on polynomials, but NURBS. And the NURBS is an abbreviation that comes from non-uniform rational B-splines. Is advanced. They are not polynomials. Let's put it this way. They are the ones that are used as a components in CAD software. So when you do the drawings in CAD software, you actually are using NURBS, non-uniform rational B-splines. That's how you define the different geometries. I'm sure the users are not aware of this thing, but that's what they use. And this is one opportunity. And you also can use trigonometric functions. You can use whatever you want. But the polynomials are pleasant because they can be differentiated so simply. That's why they are very often used. All right, so it goes like this. So you select the polynomial, and the polynomial needs to match your geometry of your elements. Let's say that if you have a spring element, you have 2 nodes. Each of the nodes has 1 degrees of freedom, meaning that they can move back and forth. So this is one motion. So then you need to get the polynomial that consists of 2 unknowns. So that's where things getting started with. So the polynomial that you can use is going to be the one that is showing in this equation. So let's see if my drawing is okay. Yeah, okay. So you have here the constant value, and then you have the value that is multiplied by x. And of course the x is, if you look at the x, is a coordinate that defines the length of the element. Now if you would have another node here in the middle, then you need to adjust your polynomial expansion accordingly. And then what you do then is that you're adding more components to your polynomial equation. So you're going to get one more unknown, which is going to be obviously A2 multiplied by x power 2. Now, how you do this selection? I don't know. I'm not sure if Suras mentioned this, but this is based on Pascal's triangle. So Pascal's triangle is the one that defines it. And now, if you select, the Pascal's triangle goes like this. So this is in two-dimensional space. And so on and so forth. It goes further and further. So if you're selecting your polynomials in order, something that you are not skipping anything here at all, you get a feature for your element that is a confirming element. And this is guaranteed that it's going to converge the correct solution. It's guaranteed that it will do so. But most of the advanced elements are not using these techniques. So they are actually skipping some of the polynomials. They might select this one, you must select, because otherwise you're not going to get the rigid body motion. This one you must select, otherwise you're not going to get the constant strain. But third component could be something that is selected here. So it's going to be x power 3. Why? Because it gives an extra boost to your elements. So it's making the elements to be more rapid convergency rate. Convergency means, you know what that means. So if you have if this is a number of elements, and this is a solution, and let's say if your correct solution is here, how fast you receive, you're getting the correct solution. That's the convergency rate. So you can speed up the convergency rate by using non-confirming elements. But you can get an element behavior that it can be surprising, because you might get an element that is fluctuating top of the correct solution. Not very common, but that's possible. And you can get even the element that is approaching the system from this side. This is not going to be an extreme case, but you need to be careful with that. You can almost get an element that is not confirming, so it cannot give you a right solution. That too is possible. But polynomial is the soul of the finite-element method. So finite-element method is all about how you're defining the life between these points called nodes. That's what it is. You got the point. Great. And now, the problem here in a polynomial is that, the unknowns here are these a's, A0, A1, A2. They don't have a clear physical interpretation. So if I give you values, okay, here's my a's. So what it means, you have no idea. You don't know how is the deformation. You don't see, you cannot have this feature to understand what they represent. That's why the polynomials are converted to be something that is expressed in terms of nodal degrees of freedom, because the nodal degrees of freedom are having the clear physical interpretation. Motion in this direction, motion in this direction, rotation, whatever is your element. So it's a clear explanation. When we're converting our polynomial to expression that is based on nodal degrees of freedom, we're going to get something that is extremely important, and that calls shape functions. Shape functions are based on polynomials, and they come because we need to express the displacement based on the nodal degrees of freedom. All this is clear. But still, I wanted to repeat this, because if you miss this concept, your life is going to be difficult. But you got the concept. I got a little bit so did we just met, or what the heck is wrong with you guys? We are not able to communicate anymore, or what? Confused. Confused. Oh yeah, I see that it is confusing because it's a big mess in my slide. Okay, all right. Now let me show you. So this is the case, the simple case to get these shape functions. In case of spring elements are linear shape functions. Not surprised, because I have only linear components in my polynomial. If I would get the more higher components, I would get the nonlinear shape functions. All right. So the beam element that you looked also during the Suras lecture, this is something that, the beam element itself, by the way, is something that is consists of 4 degrees of freedom. So 2 nodes, And both nodes has a degrees of freedom that is in transverse direction and the rotation. So this one and this one, that's a total of 4 degrees of freedom. So these do not have an axial deformation. This particular element is not capable to deform axial direction, only transverse direction. 2 ways that it can do the deformation. There could be displacement or rotation. All right, but 4 degrees of freedom. So again, I need to select my polynomial such that I have 4 unknowns. And again, unknowns are a's. So A1, excuse me, A0, A1, A2, A4, A3. And then again, I'm expressing my polynomials in terms of Noda degrees of freedom. And when I do that, I'm going to get the shape functions. And the shape functions are showing how is a displacement associated to each one of the degrees of freedom in my element. If I introduce a unit displacement to node that is located in the left side, the rest of the particles will follow this polynomial shape, which is shape function. If I introduce a unit rotation to same node, the rest, which is really the most important thing, because I need to know the rest. Actually, I don't care that much about the node itself, but the rest, what interests me. The rest will behave like this. Look at this. When you take a close look about this node here, you see that the displacement here is 0. As is angle here is a 0. So all other degrees of freedom are remaining not introduced. Here too, slope is equal to 0. Whereas here, the displacement is here is 0, slope is here 0, displacement is here 0. And the same, but for another node. How the life will be different if I'm not happy with this polynomial expansion? I'm saying, yeah, I want to give a boost. The boost that I'm not going to take this component, but I'm going to take the higher order component to get the better convergency. How they look different then. They would look like this. So now I'm selecting this polynomial, which is not confirming polynomial anymore. You see why? Because I'm skipping here. This was x power 2. And now I'm saying, let's give an extra boost. Extra boost. Again, extra boost is playing with the fire, because what I could get too is no-get elements. So this is it's like in a bodybuilding, you can do this doping. So you need to be careful with the doping, because you put too much doping to your body, you die. The same here. So you put too much doping, and the doping is higher order polynomials, you can die. They're not gonna, the element is not gonna die, but it's not capable to produce anything reasonable. The same thing here. Everything in life, actually, when you do it excessively, is not positive anymore. Here's the same thing. So you need to keep the balance. How you know the balance? You don't. You just need to divide the elements and see the few tests. And if they pass the test, those are called batch testes. And if it behaves correctly, then you're good. You have a new element. You have maybe the element that is performing better than anything before. All right, so now I changed my polynomial such that I'm not happy with the x power 2, but I'm gonna take x power 3. And also I'm gonna introduce here x power 5. So it's a really high order polynomial. And then again, same story. I'm expressing my displacement using Noda degrees of freedom, and this is how it looks like. You don't see much of a difference, but when you're comparing these two shape functions, they do look different. So this is the doped one, and this is a natural one. Which one is better? We don't know. So we should actually derive the element all the way to end, make a test, see how well it performs. But most of the modern, good elements are doped. Not necessarily much, but they are not typically not conforming elements, but they are non-conforming elements. That's a very common standard scenario. Nothing wrong. I don't know if it is wrong to do doping in a bodybuilding. I guess it is. It's illegal. Here is not even illegal. You can do it if it works. If it works, you can do it. Okay. Uh, I've been spending quite a bit of time in my life to play with the safe functions. And I can tell you why. Because, you know, this conversion, I don't know, here it is explained. This conversion from polynomial to safe function is something that you actually need to create this, you need to substitute the values of the nodal degrees of freedom to this equation, then you get the matrix that you can invert. That's the component that you can use to get the safe function. So I don't know, maybe did I tell this story when I was a postdoc in Chicago, and when I was playing with the safe functions? I guess that I did not. All right, at the time there was a plate element under development. Plate element is different than this one, because this is a 1 degrees of freedom element, so it's a line element, so it's only this direction. Plate element is something that there's another direction. So the safe functions actually are consisting of x and y's. And then this Pascal's triangle is a handy. So we were developing the element that was a really high order element, a total of 48 degrees of freedom. I'm never going to get the number, by the way. 48 degrees of freedom, meaning that the matrix that you will have to compile when you created the safe function was a dimension of 48 times 48. So that was a pretty big. So of course you cannot invert the element, the matrix that is a 48 times 48, but already that time there was a symbolic math tools. So my life at the time was that I went to my office in the morning, I started to compile the matrix. The first version of the matrix was ready at roughly at 10 o'clock. I made the inversion, and it says singular. So I was not able to invert it. There was something wrong in my polynomials. Then I make an adjustment to my polynomials. Second version was ready roughly at noon before the lunch. I make another attempt, singular. Then one more attempt before 2 o'clock, attempt, singular, and then one more before going home, singular. Day in, day out, week in, week out, month in, month out, like this. Keep on trying, like eventually it's gonna work. And I was starting to lose my hope. And one of the days, no longer singular. So we were able to create the safe functions. So did we learn anything from this story? Yeah, it makes sense to be persistent. Because it might come there, it might come. My supervisor at the time was convinced that it will come. One of these days it will come. I was myself losing the hope. No, it's never gonna come. And it's a desperate, very desperate time to come and try, not working. How actually it worked eventually was that we optimized the way the safe functions were created. Then we're so much faster, because if you're able to do 4 attempts per day, no matter how hard you work, that's not much. So we optimized it. So we were able to scan, because the Pascal triangle is big. So we were able to scan all possible combinations, and then here it was. So we were able to create the same function, 48 times 48. Okay, so that's about that story. Now I'm really losing the track here, because I'm still in the introduction of previous lecture. Things going slowly today. Remember, your responsibility was speed up. Speed up. What was that?
Our responsibility.
It's your response. Definitely your responsibility. Remember, we have these work division. I'm the here that is stories, and you're the one that is, yeah, we heard it, we don't care. Next, like what you do in a YouTube. No good. Next, and the way you saw it is this. Okay, I hear you. I see you. All right. So these were the things. Physical interpretation of safe functions. What is that the safe functions are doing? This is already something that should have checked, but I wanna really to look at this again. So this is the way that an element can deform. Defines a rotational particle, the favorite one, and then define the strain displacement relationship. No clear interpretation. And Socrates is not yet on, but it's going to be on momentarily. So let me discard this. And let me put it on. It's on. It is on. Yeah, actually it is on. Okay, so you take a look at this one, and I'm gonna keep on telling the other stories. Let me see if I
It's
can.
not on.
It's on.
It's on.
It should be
Is
on.
it two or look?
Look two. Oh, yeah, yeah, yeah. That's a good point. So this is incorrect. Look two. Look two. Because you know I want to still keep the results from the previous class on. Um, yeah. By the way, while you're doing this, so let me ask you, have you already figured out your SAML plans? You already have a place to go.
I don't know what to do, but
You know what you wanted to do, but the others are not agreeing with you. Or what's the deal?
oh, I have like summer courses I want to take, but otherwise I'm free.
So you're going to take a
Join
summer
summer.
courses.
Yeah.
But what about the work? Summer work. So we are not offering you anything.
No, I try to, but like the problem is I only want to do 2 months because I like my holidays.
Uh-huh.
And a lot of companies say like 2 months is a bit too little.
Yeah, because you need to devote your life to the company.
Yes.
So how much they expecting you to work?
Most of the time 3 to 4 months. So 2 months is like an outlier, which is why.
Really?
Like in the university, most often says like 3 months. There are a few who like say 2 months, but yeah.
Hmm. A bit surprised. Maybe because some the work that you're planning to do is needs some time, some training and stuff.
In summer work, like if you go to a company, for instance, companies most often expect more time because, of course, they train you.
Yeah,
And for them, like that's a lose if you only stay there for like as little time as
yeah.
2 months.
Could be, could be. All right. So this is what you learn from Suras. So once you have the safe functions, the rest is mechanical. You know, the safe functions is the same story than kinematics in multi-body system dynamics. So in multi-body system dynamics and in dynamics, you can define the kinematics any way you want. You're free of do any choice you want. Once you do your choice, then you need to be consistent after that. Same in a finite element method. You can select your safe functions as you want. This is kinematics. But once you have made your choice, that's where your freedom ends. You are no longer do anything else except following the rules. Following the rules meaning that you need to use a concept of virtual work or this energy balance approach to get the stiffness matrix, and you can get the mass matrices too. And this is going to be your equation of motion that defines the element dynamics. All this is very, very mechanical. They might look difficult, but there is no room for interpretation. You're just following the certain ways to make things to happen. And like what we do in our team when we are developing the new elements, everything is computed by using symbolic math tools. So there's no room for mistakes practically at all. So the only place we can do the interpretation and modifications are safe functions. Rest comes automatically out. Okay, so what comes automatically out is equation of motion. Equation of motion that described linear dynamics. Remember, linear dynamics. So we are not taking the large rotations into account, but the deformation that is small with respect to reference frame. Reference frame is, in finite element method, is you can consider that as the same that the global frame of reference in multi-body system dynamics. Okay, equation of motion is inertia forces multiplied by, plus elastic forces is equal than externally applied forces. Inertia forces is mass multiplied by acceleration. Elastic forces is the stiffness multiplied by displacement, and then externally applied forces. And now if you speak about the static deformation, static cases, then the component that is related to dynamics, you simply ignore it. What you do then is that you're solving the displacement, this nodal displacement by inverting your stiffness matrix and multiply that by external applied forces. That's how it goes. If you want to take the dynamics into account, then you need to integrate u dot, solve the u dot from this equation, then integrate u dot, I mean u dot dot, you solve from this equation, you integrate u dot, and then you get displacement. That's how it works. Exactly like it is shown here. So this is the way you go. We cannot use this kind of the approach in multi-body system dynamics. Not possible because of the dimensions. Typical finite element model consists of 1,000 degrees of freedom, 10,000 degrees of freedom, 100,000 degrees of freedom, and it's not even very uncommon to see models with the 1 million degrees of freedom, meaning that this vector here consists of 1 million components. No good, not good. Particularly when we remember what is that we aiming to do here. We aiming to describe this deformation with respect to this reference frame. So really the big trick we do in a multi-body system dynamics is that we're saying that this frame that was a global frame in finite element method, that you're no longer a global frame, but instead your body reference frame. And this frame actually can translate and can rotate. Deformation still, with respect to this reference frame, will be linear because, you know, the motion, rigid body motion, if you may, is described by using this guy. The deformation with respect to that is going to be described by u, which is this guy. You got the concept? Good. Now, this is where you see clearly that things are not matching, because this here, if you describe this in a spatial case, consists of 6 or 7 unknowns, because I need to know its translation. That's going to be 3 coordinates, and I need to know its rotation. It's going to be either 3 or 4, depending what is the way that I describe my rotation. So that's a 7. Let's say the worst possible scenario is 7. 7 versus 100,000. No, they don't match. One is too big, way too big. So we can either increase this number or decrease this number. And of course, we always select to decrease this number. How are we going to do it? We're going to introduce model reduction with help of model coordinates, and that's exactly what we're going to do. This is where we're going to take a look at the uses stuff about modal degrees of freedom. So we're simply going to take a jump from nodal degrees of freedom to modal degrees of freedom. That's what we're going to do. And right now you have no way to understand, like, what? Like, what are we going to do? So we jump from here to there. So what exactly are we doing? I will tell you that momentarily. But basically, we're going to leave the nodal degrees of freedom and start looking at the structural behavior as a structure itself. That's what we're going to do. And we're going to look at what are the possibilities that the structure itself can deform. Previously, we looked at the ways that how the single element can deform. That was based on polynomials. But when you're constructing the structure by using number of elements, like this, now we started to look at this bigger picture, how the structure itself performs, and what are the ways that the structure itself can deform. And based on that, we can move on to another space. Again, another space. Remember where we started? So we started from the polynomial unknowns, and we moved to nodal degrees of freedom. And now we take another step. We're going to move to modal degrees of freedom. You hear the difference? Nodal, modal. Because accent, you don't know, it's unclear. Sometimes you keep on telling something and people they don't understand that. The famous lecture was about the one professor, I don't tell what university, but one of the university was telling entire course about motor. And the people were like, what the heck, motor? I don't know what this is motor. And entire course was about the motor. And then then later becomes to be clear that it was motor. And people did not understood that. And the whole course was making no sense. Because of the accent.
Motor or motor?
It was a motor. It was like electric motor.
Must be an Irish company.
You know, yeah, but it can be difficult. Okay, so what we're going to do is this. Okay, here are the questions. So physical interpretation of eigenvector. You can see this later eigenvalue, how to conduct an eigenvalue analysis, a mass normalization. So here's the big deal. This is a cantilever structure that is modeled by using beam elements. I have here a total of 1, 2, 3, 4, 5 elements. Okay, and I'm looking at the static case here. So my equation is this. Stiffness matrix multiplied by displacement is equal to an external applied forces. And I would like to solve this one, which is a vector of nodal degrees of freedom. And let's create that this structure is modeled by using the elements we looked earlier. So each of these points have 2 degrees of freedom, meaning that they can have a displacement transverse direction, like this. They can go up and down, or they can rotate. So if this one here is eliminated, so I don't need to care about that. But if I look at this, it's a 2, 4, 6, 8, 10 degrees of freedom. So my system is a system that consists of 10 degrees of freedom. So what this 10 degrees of freedom means, what they represent to you, it means that the system can deform 10 different ways. Correct. So 10 different ways that the structure can deform. So what are these ways? Well, the obvious way is that, of course, it's going to act like this. The cantilever structure, for sure, if I'm going to look at the ways the structure itself can deform, this is obviously something that I'm going to find. This is the possibility that structure can deform. There's also this possibility that it can deform like a little bit like this. And then 10 additional ways that it can deform. So what we're going to do next is that we're going to identify the ways that the structure can deform. How much they deform in each of these ways, this is something that we do not know. So it's yes, sir.
I was at the first point. Will it not like rotate?
Yeah, this is considered to be connected to ground.
Okay, so it will not like move up and down, but
No, it cannot rotate either. So I'm eliminating 2 degrees of freedom away. So it's a cantilever beam. So cannot move. That's why when you look at this closely, this angle here is 0. This could be also, if this would be a beam joint, then there will be a rigid body motion in this structure. You can make a simply supported beam structure like this. But then it behaves differently again. Okay, but now we're looking at the cantilever beam. Now I have 10 different ways that the structure can deform. Unclear how much each of the ways contributes. But that's okay, because what I can do is that I can say, okay, this is the way that the structure can deform. How much it deforms in this way, that's going to be my new unknown. Let's call that as a question mark number 1. This is the second way that it can deform. This is going to be question mark number 2. And I'm going to have a total of 10 different question marks. Each of them associated to different ways that the structure can deform. And if I look at my original vector of my nodal degrees of freedom, which consists of 10 units, so it was a ux1, u theta 1, so on and so forth, until the 10th component. This can be now represented in a way that this is my matrix, that each of the columns describes the way the structure can deform. There's going to be a total of 10 different ways, multiplied by 10 unknowns. And now I'm all of a sudden calling these unknowns by P, so I'm replacing question marks by P. So it's P1 to P10. This representation is something that I lose no information whatsoever. So it's exactly modal reduction comes into play when I'm saying that actually some of the modes, some of the ways structure can deform is not equally important. Some of them are less important than others. So you do the real discrimination. You're saying some of the modes that I don't like you. Actually, I hate you. I hate you so much that I'm going to take you off the picture. I'm going to kick you off because I hate you so much, because you're delivering so little to my life. That's the reason that I hate you. And then the mode say, I'm going to pack my stuff and I'm going to go. And they go. And when they go, your model gets smaller because you get rid of the not productive persons of your community. Real discrimination. Awful life. Awful things that happens in engineering. But it is what it is. It is what it is. It's like this nature selection. Nature is selecting the strongest member of the community, leaving rest with the no attention. Same here. Okay, so some of them, number 3 is not delivering much to your life. You say, number 3, take your stuff and leave. Number 3 will disappear here too. Number 7, take your stuff and leave. Number 7 leaves. And that's the way you reduce your model. So you get started from 10, you end up to have something less than a 10. Of course, you're going to compromise your accuracy, but not much. Because it's quite surprising that when you look at this, how much each of the modes are delivering, how much they are contributing, only a handful of them are responsible of the majority of the deformation. Rest, they are not very important. You can let them go. You lose nothing. Yes?
You can also reduce the degrees of freedom.
So you
Reduce the degrees of freedom. If you write out the 3 or the 7, then you have more degrees of freedom than on the other side in the matrix.
Yeah, so what happens is that, if you get started here in a 10, you have here this 10. So this is still a 10 units. I said this is equal. Now I'm saying that is roughly same than the mode. Let's call this mode like this. I don't know what the heck is this notation. Is this a C or whatever? Okay, so this is a mathematical, numerical description of first mode, and then corresponding amplification, plus second one corresponding amplification. And then I'm saying, okay, rest, they can go. The only one that I'm going to take as a part of my team is a 10. So now I have 1, 2, and 10. Rest, I don't care anymore. I let them go. 7 going to disappear. So I started with the 10, and now I only have 3 left. Of course, I'm going to, I'm not as strong as I was because I'm losing 7 members of my team. But again, these 7 members are not productive members. They produce, but very little, very, very little. And actually, there is a way to look at this thing because you can keep all the modes in your model and you can compute the deformation and you can take a look at the strain energy each of the modes are delivering to your system. And it's quite surprising that majority of the energy is delivered by, let's say, 4 modes. Rest are not so significant. And now you can have a model that consists of 100,000 degrees of freedom. Still, you only take few of them, and rest can go. We still have the Nora degrees of freedom because remember, each of these modes are representing how the entire structure behaves. So we still have the way to see how is a Nora degrees of freedom when we look at these modes. That's the model reduction. That's what it's about. Okay, how is that we can select these modes? The most common way is to conduct eigenvalue analysis because eigenvalue gives you an understanding about how is a feature of the structure. Okay, it is like if I have this pen, it would be nice to know what is the lowest natural frequency of this pen and the corresponding deformation. Second lowest frequency of the pen and the corresponding deformation mode and so on and so forth. Again, if I would have a 10 Nora degrees of freedom, I would get 10 eigenvalues and eigenvectors out of my system. And if I would have 100,000 degrees of freedom, I would get, in theory, I could extract 100,000 modes and corresponding eigenvalues, corresponding frequencies. It's possible, but I'm not going to do it. I'm going to just compute some of them and leave rest with no attention. That's what I'm doing. And I'm going to do this selection of, to see how the structure behaves by using eigenvalue analysis. An eigenvalue analysis is nothing but look at the feature of the structure. This is, by the way, extremely important to understand because it physically hurts me, really physically hurts me when I hear students who say that, okay, here's my eigenvector and it's explaining me this absolute deformation, this and that, because it's nothing but the way the structure can deform, nothing else. It's nothing to do with the actual values. So it's just the way that can be multiplied by any multiplication you want. That's what it is. How can this is the case? The eigenvalue analysis you conduct for the system that you have no forces, you just have the feature of the structure. The feature of the structure is inertia and elastic. Inertia forces, elastic forces. It's like, if you look at the eigenvalue for the mass spring system, you need to know the spring coefficient and the mass itself. Same here. But this is multi-degrees of freedom system because you have not just a single mass, but the number of mass degrees of freedom. And not just a single spring coefficient, but the stiffness matrix that consists of multiple degrees of freedom. So that's why I get them a lot of values, a lot of eigenvalues, a lot of eigenvectors. Okay. In the beginning of conducting eigenvalue analysis, you take the forces off. You say, I don't care about the forces because I'm not here after the actual responses, but the feature of my structure. That's why you say, hey, force, I'm going to put you to 0. I'm just going to look at how is the structure itself. Okay? So when you do this thing, then you know that there is this analytical solution that is not easy, not pleasant. It's this phi, which is a vector, consists of equal number of degrees of freedom than not a degrees of freedom, and then the rest of the solution goes like this. Very, very painful. But when you substitute this to your original equation, you can put it in writing like this. You have here stiffness matrix, then you have this omega, which is your eigenvalue, same than natural frequency. You have multiple eigenfrequencies in your system, and then you have here the way the structure deforms in one single eigenvalue. Very confusing, but we're going to take a look at this a little while. Okay, so first thing you do, you're solving this guy, natural frequencies, eigenvalues of your structure. What is the frequencies that are frequency content of your structure? And you can select this one by taking the first part of the equation and computing the determinant of the first part of the equation, which you don't do in real life. There are more advanced algorithms, but just sake of simplicity, we say determinant. For sure, you don't do this in a big science system, but you use a Lanczos subspace and more advanced techniques, which is a numerical techniques. We don't care about that because we want to learn the big picture here. Okay, you set the determinant of this, you're able to compute number of eigenvalues. How many? As many you have degrees of freedom. And then you can take each one of them at the time, put it back to this equation, and solve the eigenvector, which is the way structure can deform. Now you have a combination of eigenvalues and eigenvectors. What we are really interested in is eigenvectors. Eigenvalues, we don't care that much. Actually, we don't care at all. Okay, that's an eigenvalue analysis. Now, finite element model depicted below consists of m number of elements, n degrees of freedom. The model can be used to solve how many eigenvalues. Is it going to be equal than the number of elements? Is it going to be equal than the number of degrees of freedom? Is it going to be elements minus number of degrees of freedom, elements plus number of degrees of freedom? One only makes sense. Others makes no sense. Which one makes sense? Yeah, because remember what I said. You get this as many as this. You get equal amount of eigenvalues than your not a degrees of freedom. That's what you can get. Elements has nothing to do with this business because element can have a multiple degrees of freedom. That doesn't make any difference. And the subtraction summation makes no sense. Okay, so let me take a look. What the heck? This clock is incorrect. I'm losing time big time. And your responsibility. I'm blaming you, each of you, because where is your sign? Okay. We are in slide number 13. Oh my God, this is a big problem. Big problem. Okay, so we got 21 answers. So let me solve this one. Oh, you don't see this. Okay. What do you think the success rate is going to be in this physical interpretation of safe functions?
78.
Yeah, it's going to be low. It's going to be low. It's not going to be very high, but I'm thinking that's 70, you said 78, 71. Very close to that. Very close. The next one is going to be harder, so I'm expecting success rate to be less than 60, 60. What do you think? I like your can-do attitude. Okay. All right, I'll leave this, and I'm going to go back to my slides. Just to make sure that you know that what we are speaking when we are saying eigenvalue and eigenvector, I want to make sure that you understand what I'm saying here because, sorry, I made a mistake here. I'm sure this is explained to you already in where did they explain in a junior high school, high school. When you heard the first time about eigenvalues and eigenvectors,
Yeah.
that here in university.
Yeah.
I thought that they explaining those already in a high school.
Yeah.
They don't.
We taught in university, but not that deeply. Like we didn't learn about the applications.
Okay, all right. Okay. All right, the eigenvalue, natural frequency means that each of the structures have multiple points where the deformation becomes to be very high if you exciting the structure in certain way by using the same frequency than the natural frequency. Example is this. No examples. Yep. There is an example. Example is this, cantilever beam. Okay, so cantilever beam, this cantilever beam, this is a system that is continuous system. So in theory, this consists of infinite number of eigenvalues, natural frequencies. Lowest, when there is a boundary condition like this, the lowest is the one that you see here. One. This is the lowest. And if I keep on exciting this structure by using this, yeah, I don't have a talent to do that. But if I would do the excitation using the same frequency than this, the amplitude in theory becomes to be infinite. Not in practice, because, there's a limit. Roof and the floor and also the length of the stick, it cannot be infinite. But in theory, it becomes to be very, very high. So this is the lowest frequency and corresponding deformation mode. And then there's many, many others. But you need to be exciting the structure where the displacement actually exists. Because if you excite the structure here, no reaction. So nothing going to happen. So that's what is an eigenvalue. Now let me demonstrate that by using this animation. This movie, this is actually a really nice one. No, it shouldn't be a picture. Okay, I need to send you this animation. There will be another. I think that I made a mistake when I put this PowerPoint presentation on. No, this is a picture. You're right.
There is a sign of video on the left, bottom left.
But here, left here.
I think it's taken, yeah.
Okay. So, hmm. So can you see? All right, I cannot show this.
Not anymore, yeah.
Okay, I cannot show this. Here's another one. Okay, this is the lowest natural frequency of the roll structure, and it's a banana shape. Banana shape, another direction. Because in three-dimensional structures, you have this is the lowest, same but another direction. Because this is symmetrical structure, this is the second lowest. And then the more complicated ones. I don't want to show any more complicated. Not that I couldn't, but I just don't want to show it. It's just, you can see it here. This is how they look like. You have the many of them. Again, as many of your nodal degrees of freedom. So many of them. The point of the model reduction is that some of them are not important. Some of them I couldn't care less because they give me no extra, well, let's say, additional information. Or they do, but the amount of additional information they deliver is insignificant. And that's why I can ignore them. I cannot ignore nodes, because if I do that, then maybe I'm going to get the finite seven model that is not converged. That's not okay. I cannot use that. That's not possible. But I can use this model reduction technique. So I can build the model by using a significant, enough elements to make sure that my solution is correct. And then I can reduce modes without losing significant amount of accuracy. That's what it is. Okay, this is the main message that what I wanted to deliver today. So you got this concept. Good. Okay, then I have more animations. Some of them, they're showing like the way the structure can deform. But just to give you an idea, like how insignificant some of the modes are. This is the structure, this simple hydraulic driven crane. So this is obviously very significant deformation mode, particularly if the system is loaded in this upright direction. This one here, even though that this introduced the lower frequency, probably not significant because the deformation is in transverse direction with respect to loading condition. So there's no forces that introduce the deformation like this. Here, this definitely is something that there are forces in this direction. You keep on adding these modes, you get more and more accurate description. Typically 1 is not enough, 2 is giving you better, 3 is better. You keep on adding and then you're going to get the acceptable solution. But then this structure, because it's made by solid element, some of the deformation modes are like this. You would like to have this kind of the player in your team. No, you don't want to have a player like this because this is obviously a free rider. This guy is delivering very little to you. This, come on, can he deserve to live? No, you need to take him away from the picture because the deformation is the deformation that takes place when there is this axle in this tonal bearing, and the axle is getting bigger and smaller. Come on, how you can even introduce the forces like that? Well, the magnet can do it, but other than that, this is no way that you can have a forces like this. Forget about the guy like this. Let him go. Then, what about this? You like this guy? Yeah, why not? It could be important if you look at the local deformation, but seriously, not so productive. Not so productive. Look at this, the ones that were really carrying the most of the load. These big deformation we looked in the previous slide. What about this one? Even the frequency is so high, because if I read correctly, this frequency is 2,700 and something hertz, so it's a really high frequency.
Look at the upper one. 12,000.
12,000. 12,000. Definitely we don't need this person. Let him go. Okay. This one here, 7, maybe. I don't know. Hard to say. Maybe. Okay. All right. Now the beauty. Let me summarize this model reduction. The beauty is this. I know when I click this, it's not going to work, so let me take this off. Okay, by the way, I never asked, like, would you like to have a break today?
No, I just
No break.
yeah, I have a lecture right after this, and we need to eat.
Okay, so then you have some time to, are you planning to have a lunch after this? Good. Sounds good. Okay, now comes something very emotional. Very emotional. Many people are crying when they see this. So are you ready to see this? Take a deep breath. One more time. Now you're ready to see something amazing. Here it is, something amazing. Okay. Something amazing is this. So this is the original equation of motion. This one. Okay, not willing to write anymore. This system is stuck. Let me put it on. Highlight is delayed, but it will come. Now it will come. Here one more time. I don't know why that I'm not able to do drawings anymore. This slide is stuck, so I'm not able to move any more back and forth. But the big, you don't even see this anymore. So we're obviously going in the wrong direction. It works. Okay, so let me explain it here. This is the original equation of motion. So we have still a very high number of degrees of freedom. So we have here inertial forces, elastic forces, externally applied forces. Each of them are associated to a very high number of degrees of freedom. So if the finite element model consists of 100,000 degrees of freedom, which is not unusual, then the matrix dimensions will be 100,000 multiplied by 100,000. So very, very big. So what we do then is that we're moving from nodal space to modal space by conducting the eigenvalue analysis and corresponding ways the structure can deform, eigenvectors. And now using these eigenvectors and their multiplication, amplification would be a better way to say, I can write the equation of motion as it is shown here. You don't see how it, because I'm not able to use my pen, you don't see how this went, but this is the way it looked now. Now your model size is significantly reduced, really significantly. Because if this was originally, no, if the equation of motion above was originally 100,000 unknowns. Now if you select 5 modes, then your corresponding inertial forces, which is a mass matrix multiplied by modal coordinates, will be 5 times 5. So really significant reduction. And your elastic forces will be stiffness matrix where the dimensions are 5 times 5. And not just that, there is even bigger story than that. You know, I came down a lot from the size. And even the structure, it becomes to be way more pleasant. Because when I'm selecting my modes such that they are orthogonal, they are not related to each other, which is always the case when you conduct an eigenvalue analysis, then the mass and the stiffness becomes to be diagonal, meaning that modes has no relation to each other, as is the case in nodal degrees of freedom. Nodal degrees of freedom, you always have to solve as an entire system. You are not allowed to take one single nodal degrees of freedom and solve that, knowing nothing about others. Just that is not possible. Why? Because mass matrix and the stiffness matrix in the finite element model is block diagonal. So they have more components than the diagonal components. Now, when I'm using my modal reduction, I only have diagonal mass and diagonal stiffness, meaning that I can select the mode number 10 solve the mode number 10 knowing nothing but the mode number 10, knowing nothing about the other modes. That's possible because of this orthogonality. And this is beautiful. You know, some professors are calling this as a, how many miracles we have in this planet? How many official miracles we have in the planet? Because there are like 7 miracles in the planet, is it? So this is like 8th miracle of this planet. So you know more miracles than others. You should be happy. Impressed? Quite impressed. Okay, let's practice. This guy is somehow, I don't know what the heck is wrong with this slide, but it's completely stuck. I cannot open that. Okay, let me show you an example. I don't know where I am now. Okay.
I have a suggestion.
About this,
Yeah.
what's your proposal?
Just to extend, and then also maybe share the second screen, move the screen to the second one.
But I cannot do the drawings.
You can, then PowerPoint should have like the option to have you like also see the screen on the main one.
But what about the ones that are following me online? Can they see me too?
Yeah, OBS if you change it to.
Yeah. So I can select which screen I'm selecting in my OBS. Point ticket. I got it. Because still this pane will, you know, if really able to make a drawings. Yeah, like I'm able to do it now. It's a big benefit. It's coming. For sure it's coming. Okay, so what I did, let me summarize this. Okay, so here is still this equation of motion is expressed in terms of nodal degrees of freedom. I'm using this relation where this is my deformation modes. Not all possible them, but some of them. These are the corresponding amplifications called P's, modal coordinates. When I'm using this relation, you know, I can, you know, take this, substitute this to my equation. So my equation, because the relation is linear, it reads like this. P dot dot plus K P, this is just P and forces. But the forces are now expressed by using nodal coordinates. Everything else is modal coordinates. So I need to multiply the whole equation one more time by transpose of the modes. And when I do that, then sorry about my lousy handwriting, but this is how it looks. This is going to be my new equation of motion. And then this is now the forces are in the modal coordinates. This is diagonal, and then I have very few components left. This is the trick that I did. And this is how it reads. This is my new equation of motion. Now I can start using this as a part of my multi-body mode model, because now I can reduce the modes, deformation modes, to be reasonable. 100, 10, 1,000, whatever is my computational capacity. But previously, when we speak about 100,000, that's off the picture, not possible. Okay, let's look at shortly about the eigenvalue thing, and then I have one more in-class quiz. I've got to speed up a bit. Here's my structure that is spring elements. Remember that the spring elements is something that can move only and only in axial direction. So each of the nodes has this degrees of freedom. So they can move left and right. They cannot move in a transverse direction. They cannot rotate. Okay? I have here 1, 2, 3 elements. 3 elements. And I'm constructing my mass matrix such that I'm creating the stiffness matrix for each of these 3 elements. And I'm constructing my structure such that I'm creating this block diagonal representation. This is my first stiffness matrix, my second, and my third. And you see that they're overlapping the places where the nodes are shared. This is how the finite element models are constructed. Okay, but you see that this is not diagonal representation, but block diagonal representation. Meaning that, you know, if I wanted to solve one nodal degrees of freedom, I need to know the others too, because this is not diagonal. Same is my mass matrix. So this is block diagonal representation again. Here's my system. First, what I'm doing is that I'm solving the eigenvalues. Nothing but eigenvalues. This is the natural frequency, right? So I take my, this is my equation. I take my stiffness, I take my mass, and this is my lambda. Now lambda is equal than omega 2. I'm solving my lambdas here by taking determinant out of the matrix, which is a 4 by 4. Okay? I'm going to get the polynomial like this, which is a fourth order polynomial because lambda is here, 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 and here. So this is obviously fourth order polynomial. All right? So fourth order polynomial, how many times that crosses the 0? 4 times. So these 4 times are my eigenvalues. I'm solving these times that is crossing the 0, and these values are 0, 12, 60, 120. And you can compute the natural frequency based on that using this equation. Okay, what this number 1 means, that the frequency is 0. 0 frequency, 0 hertz. What it means? What is the physical interpretation of that? Doesn't move. Very correct. Others, you agree with that? So it doesn't move. Okay, the correct answer is that it doesn't deform. It moves. So it moves. So the problem is that it moves as a rigid body like this, but it's not deforming. You see when I'm stretching this. You see that when I'm stretching, yes? Like this. Okay, so it's not deforming, but it's moving. It's a rigid body motion. Okay, rest are describing the mode. Rest are describing the other, deformation. Now, how are these deformations? I can find them by substituting my eigenvalue one at a time to this equation. One at a time. First one, I'm going to take this, just to show you an example. I'm going to take a number 12, put it there. It's going to give me this equation. This is 4 equations, 4 unknowns. And once I'm solving my unknowns, it's going to give me the values like this. This is the way structure deforms. Nothing but the way. Absolutely not absolute values, because I can multiply these numbers any scalar I want. Any scalar I want. 100,000, 1 million, still going to fulfill my equation. So it's just the way structure deforms. Let's look at the way. Okay, if this is my original structure, the first node is moving negative 2 units, so it's going to go here. Second mode is moving negative but a little less, like here. Third one is moving positive, and fourth one is moving positive. So it's moving like this. Makes sense. This is your lowest deformation mode, and when you compare the fourth one, it's going to be the deformation where if this is original structure, and the first one is moving here, second one is moving here, then the third one is moving here, then this one is moving here. It's like a wave is traveling within this structure. That's an interpretation of that. Each one of them are associated to eigenvalue. Only what we care is deformation mode, which is absolutely not absolute deformation, but the way that structure can deform. Absolutely not absolute. Not a very clear language, but you got my point. Okay. All right. I know you guys are getting tired, so physical interpretation of an eigenvector. Relative displacement. Relative displacement of not a degrees of freedom. Absolute displacement of not a degrees of freedom. Strain distribution within the structure. No clear interpretation. What is the right one? Okay, and let me take this off. And then soon we are able to close today's lecture. Okay. So what do you think about the second in-class quiz? What's going to be the success rate? 85, that high? Because I'm thinking 60. 60. More about 60. 76. Not bad. Okay, next one. This, I, okay, I don't know if I'm ready to go to the in-class quiz because remember what I say about absolutely not absolute.
You might have fooled some people.
So I think this is making people confused.
Yes.
No way absolute. No way absolute. They're never telling anything about absolute. Why? Because we don't even have forces in the game. The forces are missing. So how come they can explain something absolute? They cannot.
Can match the absolute.
But you can compute it later, but not right now, because we're still looking at the feature of the structure. It's only the feature of the structure this time. Then later we can extend this any direction we want. Okay, so 7, I'm going to get back to this momentarily. And I'm going to keep this presentation mode for a little while to make sure that we can close the story. You know, like I say, so the way the structure can deform. Now this way can be multiplied by any scalar you want. This actually has a call, this scaling has a name, and it's called normalization. Because it's certain benefit if you normalize your deformation with respect to your mass or with respect to your stiffness. Simply because, you know, when you do so, you can get the numbers that are more pleasant to your computational performance, in terms of your computational performance. And remember, these deformation modes we can multiply or we can play as we want, because it's only the way. If this is the way, and I can multiply this more, it's still a way, nothing but the way. So it could be this way, this way, this way, so it's all the time same. Now, when I'm multiplying these deformation modes by certain values, it is called normalization. When I'm normalizing them in such the way that the mass matrix becomes to be identity matrix, it is called mass normalization. When I do so, the only thing left me to do is to figure out what number these modes need to be multiplied to make sure that each of the modes, when I multiply them by mass matrix, gives me the value 1. All right, so my first mode is this one, -2, -1, 1, 2, multiplied by my unknown multiplication factor. And then is my second mode here, an unknown multiplication factor, and then I'll set this equation to be equal to 0. And the question is, what this multiplication factor is supposed to be? Answer is square root 1 divided by 5. Again, I'm scaling my numbers, nothing but the scaling. This is called mass normalization. It could be stiffness normalization. Some people prefer to do that. It really doesn't really depend what you do, but good you to be aware that this is just a scaling thing. Now I'm scaling my second mode, and it turned out the scaling number is actually 1. So this is my scaled deformation modes. And now when I multiply these by my original stiffness matrix, I got identity matrix. And when I multiply them by my original stiffness matrix, I got my eigenvalues to my diagonal terms. So it is beneficial in that sense. With that, let me see. All right, and then this is the way you can solve the system. So you can take, you know, this is stiffness multiplied by modes. Excuse me, elastic inertia forces multiplied by acceleration of modes, elastic forces by my modes, external applied forces. And these are your two equations that you can solve to get the response. Of course, you can get the final response when you sum these modes together, modal coordinates together, P1, P2. And that's how it goes. Okay, end of the story. And then when you want to get back to yourself from the deformation mode, again, you're using these, when you know this, when you solve these ones, you can get back to the Noether degrees of freedom, again, by using your deformations. Simple like that. Not simple like that, but that's how it works. Then, one more story. Okay, shortly, this one more story. You know, I'm looking here at a connection rod. So the connection rod that is connecting my crankshaft and the piston body. And they are revolve joined in both ends of the connection rod. What could be the proper reference condition to my eigenvalue analysis? Because if not having reference condition, I mean boundary condition in my finite element model, then I get these zero frequencies that are introduced in the rigid body motion. I can take them manually out, so that's possible. But my question is that if you would need to define the deformation mode for the connection rod, how you would define boundary condition in your finite element model? Options are no boundary condition. You throw this connection rod to space, and then it deforms as a space body. Or you introduce a simply supported beam connection, like this is displacement is connected. Here, displacement are limited except the motion in axial direction, or is it going to be the cantilever beam? Those are the options. Which one is the correct way? What about the others? What do you feel? B. What else? B. I'm saying A. What about the rest? Are you with me or with them? Ah, clever. But I'm changing my mind. I'm saying C. You with me or with the rest? Okay, answer is every single one is correct. This is very confusing. Like, what? How come every single one can be correct? This needs some serious thinking. Because actually, what are you really after is how the deformation look, how is the deformation mode. And this is just the same deformation, but they are like lifted up or lowered down a bit, but the shape is still the same. And even here, the shape is not much of a difference. The shape is still the same. This is something that is quite confusing, but there has been a numerical example where the boundary condition is made by using these three different conditions, and the response is almost same in each of the cases. Why? Because what matters for us is that how is it we can reach the final destination? Okay, this is in-class quiz. Final destination. Let me show this final destination picture to you. Maybe this is the best. Now, in the first case, so let's say that I'm interested in a point particle that is located here in the free end of the, well, let's say in the middle is the best, middle of the connection rod here. I promise we're gonna, let me finish this story, okay? And then we go. Okay, this is what we're interested in. And now we have here the reference coordinate system that is located here. First, what we're gonna do in the multi-body dynamics, we're gonna travel to this body reference coordinate system with help of vector r, okay? And then for vector r, we're gonna go to this place here. This is how it is in this first scenario. Second scenario is a little different because we're gonna have the reference coordinate system that is located here, but you see that this is exactly the same condition. Now you're not going here, but instead you're going here. And here you're traveling again the same, exactly same point. The difference actually is just the road you take, final destination, all the time same. It's so confusing that I don't know. This is so weird because you know that each of these are associated to different frequencies. But this is the difference between the linear dynamics and nonlinear dynamics. Because in nonlinear dynamics, we are really interested about the final destination. Linear dynamics is about the pieces of journey, pieces of the trip. And the pieces of the trip, they might look different depending what road you take. Bosch is here, so we need to close. And the Bosch is so vicious and strong, so we need to better obey.
What is the next quiz? Are three of the quiz answers the next quiz correct?
So you want to see how well we perform. This one.
Yeah.
Oh my God, take a picture, right now. It's here, it is here. One more, like this. Very good, very good. Thank you, people. Make my day. Not my day, my week, my month, my year. my life. Fantastic. Really nice. Thank you so much. This is definitely where we're gonna close. Definitely. Respect. Thanks, guys. See you next week.
The other methods of sharing screen.
Okay, so you want to show it to me. Okay, so let me, hold on. Let me stop streaming. So it says that others are not able to see this.